stone beam on the right-hand side is the lowest carbon, and that's why we are here talking about stone, particularly in the context of global warming.
Can we dive in on this one?
Back to you.
Okay. So 2017, this code was adopted across the world, EN 15978. Try and burn it into your retinas, which divided up the embodied carbon of a building across its lifespan into sections A, B, and C. A is the red and the orange, which is materials and the construction, so the processing of those materials, the making of those materials, and eventually transporting them to site and constructing it. The green one is what happens to those materials at the end of life of that building. You add those together, this is 2017, you add those together, they're about 60% of the embodied carbon of the building across its lifespan. So the operational carbon, the light switching on, the heating and so on, is about 40%, 2017. When I was a student, the operational carbon was about 80%. So the materials about maximum 20%, so my tutors told me. Why has that changed? Well, we insulate buildings better. We've got double glazing everywhere, lots of insulation, and the equipment's got more efficient. So the amount of energy we spend to heat, light, and so on, power everything in our building, is reduced across its lifespan, while the materials haven't. We're still making everything with steel frames, reinforced concrete, aluminium, so on and so forth. So as that operational carbon reduces, the materials become ever more important. At the same time, 2017, the Institute of the British Services Research Institute and the University of Bath created what's called the Inventory of Carbon and Energy, which used to have, well, it does have the acronym ICE, but perhaps we shouldn't be alluding to that, which gives you the embodied carbon of all materials and construction. Here, we just listed some of them, and we put them in a traffic light system, a color-coded system, with the worst performing at the top, the best at the bottom. In the UK, we have traffic light systems. When you go to the supermarket, you know what you're putting in your trolley: highly processed salamis, at the other end, a bit of kale. So at the end of your journey, your trolley is either full of cigars, whiskey, and highly processed salami, while the next door neighbor has got their kale. And one will have fantastic parties, you'll really enjoy yourself, but you know they're not going to be around for long, while the other one, you'll never go around to their boiled kale dinners parties. So the argument is your building materials have exactly the same trolley. Fill them up with plenty of healthy kale, but maybe you have a sprinkling of your deep-fried lardons on top of your kale to make it a bit more tasty, without exceeding the embodied carbon. But if you look at the bottom, all your biomass materials are carbon sequestrating, so they've disaggregated carbon dioxide via photosynthesis, twice the amount of mass of CO2 molecule disaggregated to make them the same weight, mass of a piece of timber, a complex sugar that's eventually timber. So it's highly carbon dioxide hungry. So the thought experiment should be, let's make everything out of timber. And then we're taking CO2 out of the atmosphere, but we can't. And as Steve has just shown in that previous slide, we shouldn't in some areas. It's far more efficient to use small amounts of stone than lots and lots of timber. If you go up that list, what's the next thing after timber? You can't make your building 100% out of timber. Your wiring, your plumbing, your glazing. What's the next material? Maybe your foundations? Stone. Stone is zero carbon because it's made hundreds of millions of years ago. Or by Mount Etna last year. And we've used stone that's come out of Mount Etna. It's constantly there. The entire globe is molten magma, and we live on that thin, cooled crust on the outside. We're never going to run out of stone. Yep. We can't possibly use enough of it.
I could say that we're never going to run out of slides.
Right. I'm going to drag this out.
You were going to anyway.
So together we created this, just a couple of calculations on an Excel spreadsheet that you can plug in the volume of materials you have in your design, and it'll generate the embodied carbon of your building. And you use this as an iteration tool. Oh, I've gone over. Why have I gone over? Because I've used a steel frame. Can I substitute that steel frame with timber or stone? Yes, I can. What happens? Bang, it collapses. You keep doing that. with your materials plus your operational carbon, how can you make operational carbon negative? You have so much renewables on site, more than you need, you give it to your neighbor or sell it to your neighbor, which means they're drawing less from the grid that's dependent on fossil fuels. That's a double negative, one in your embodied materials as well as your operational carbon. Yeah, so these are iterations in terms of the design of substituting materials and eventually going negative. And then studies we did for a number of developers to show if they replace their superstructural frames, what happens. Now at that time, that was some time ago, we hadn't quite got as far as stone foundations, but we're beginning to experiment with that because obviously there's quite a lot of concrete in foundations normally. Off you go.
So people have said in the past, it's all very well building with stone, but what happens when the stone runs out? And when they say that, I kind of imagine a cluster of buildings floating around the sun that we've consumed the entire Earth. How much stone do you really need? If every person of the 8 billion people on the planet had a 5 meter by 5 meter by 200 millimeter slab, it's a quarry 40 kilometers square and 20 meters deep. So the volume of material that we need to edify is absolutely tiny compared to the geological provision of stone.
But I think also on anything to do with geology and what stone is about, I think we just need to remember that, you know, the famous geologist Hutton, Scottish geologist Hutton used to say, we are a succession of worlds. So stone is continuing being made as we speak. You know, there's a little grain at the top of the Andes falling down the Amazon and then going to finish on a beach and it's going to prepare the next sedimentary stone. So of course, it's a slow process, and it's going to get 100 million years before you got your next slice of limestone. But still, I think it's a bit pretentious of us to think that, you know, as you suggested, we are going to dig the whole Earth and the whole lithosphere, you know, in the next 200 years. No, we are talking at the moment. There is stone being made all around us. We don't see it, but it's happening. And of course, something that is important is that it's something that disappeared recently in the last 100 years. But any large stone building was a quarry to be. Okay, so do not think of stone, I feed the stone, next time I'm going to crush it and use it for something else. As per this quarry, you can see that, of course, you can extract it, but also you can pass this big piece of stone from one generation to the other. And that is something that we do not forget. It is, we've got a responsibility with that continuous ecosystem.
And remember that, you know, people always ask,
That's interesting.
Is there enough stone? Will we run out? And surely the planet will be covered in quarries. And you have to ask them, well, where do you think steel comes from? Where do you think concrete comes from? Steel takes about 8 ingredients, minimum of 8 ingredients, all of which are extractive. In other words, they require quarries. Our mission isn't to eliminate steel or concrete. It's simply to say, step back. Do you actually need that much steel and concrete? So you limit the amount that's produced to what's absolutely necessary. And have one stone quarry that would be the equivalent of the 8 quarries that are for steel. And you remember also that cement is made of limestone and a bunch of other ingredients, all of which are extractive. And the cement is the limestone that's crushed, smashed, burnt, mixed with other materials, by which time I'm probably nicking your slide, is lost 70% of its strength. Please take over.
That is interesting, I mean, that is interesting.
Well, so we were also interested, it's extractive, what about the land use?
Was that our safe word? We should swap over when you say that's interesting.
Sorry, we've got a safe words so that we know when to shift from one other. So I have to be like that saying, this is interesting.
Yeah, this is getting really interesting.
And Steve has
that
to say,
was getting really interesting.
And then we've got safe word 2, which
I'm
is
interested.
shut up. We hope we are not going
Far
to go
away.
So this slide is looking at this slide is looking at the comparison between the traditional solution to building in a green way, which is timber and stone. And on the right-hand side is the quarry in the south of France, and you can see very clearly illustrated a tree grows about 1.5 cubic meters of useful timber with a strength of 7 newtons over about 40 years. So we made up this unit, 0.9 meter cubed newtons per year. So it's how strong over what period of time. Underneath the tree is 500 cubic meters of 100 newtons per millimeter squared material that you can extract in about 3 months. So nearly half a million times better in terms of land use to quarry stone than it is to grow trees.
Right. Okay. You cannot say anything because you don't know what I'm doing.
This is going to be interesting.
Right. Okay. I'm sure you would have all recognized the signature of Imhotep. Okay. Yes.
You're waiting for them to say.
Thank you. Thank you. So yes, so of course there is a bit of a legend. There is a bit of sometimes misinterpretation of who Imhotep was, but he was the big architect of the pyramid of Djoser and in Egypt and the area around Djoser. But the sort of story about it was that when I visited Djoser, my friend stonemason just showed me that beautiful realization of that wall with that, how do you call that, reed lotus-like, how do you call that, column, pilaster against that wall. And apparently it's Imhotep who decided to, in fact, change the matsaba and this tomb that was made with clay, with lotus reeds and so on, and just to kind of make it worse what Pharaoh is, and that his name was going to be carried through eternity. And what's interesting is that you have the first expression of what is a pilaster and a column, but it shows an understanding. It shows first that behind any realization before us, there is tools behind it and knowledge, and I think it's really show a good knowledge of tools, a good knowledge also of engineering, the way you are going to put one stone on top of each other, and of course the aesthetic of it, and the funny bits being, being a reed that's going to be put in a sort of skeuomorphism in stone. So a reed that works really well in flexion, in fact, or I would say, Steve, and stone works well in compression. So you've got something that should work in flexion, which is suddenly working in compression. So I think that something that we all need to not to forget is that behind any transformation of a material, natural material, there is the need of tools, and tools is very important. And again, what you can see here is a tool, tools that allow to transform that material. And we don't know if they had the tools and suddenly say we can change the condition of stone and make it that way, or if they wanted to make that transformation. How to call that in stone and develop the tool to make it happen. So that I do not know. But then after that, when you look at this sort of very, I hope there's no ancient Egyptian in the room, but when you look at the old Egyptian way of building, it was pretty simple and very static. You stack one stone on top of each other, and if you don't have a lintel that is 6 meters long, you go to the local quarry, extract your 6 meter long piece of stone, and just put it on top of your columns. What's happening with the Roman is that they start to develop a system of well-defined prefabrication, well-understood geometry, so that they can roll out not only their system, their political system, social system, and so on, but also a kind of kit of part to build from Britain to Tunisia. I'm sorry, I totally forget the El Jem. I think it's El Jem in Tunisia. So when I visited this beautiful ruins of Colosseum, what you can see is that compared to, for example, Egyptian architecture, it will be extremely static and, as I say, very horizontal and vertical. And there you start to have arches. And arches come assembly, geometry, etc. And of course, it comes with a sort of very first, what you are talking about, orders and design of orders with a book, Vitruvius, of course. And I think we can start to see a sort of the very beginning of a sort of academia. Academic design coming through this sort of Roman construction, as I say, made of assembly of stone that's going to stay together up in the air. And something that is totally at the opposite of what the Roman did was, of course, the Gothic, right? So, and I do feel, you know, when we're talking with Steve and Amin, we try to revive this sort of Gothic feel to architecture, engineering, and so forth. Because here you've got the Amiens Cathedral that was built by master builder Renaud de Cormont starting in 1220. But this is an amazing piece of engineering. I mean, you know, it's been discussed many times at length, and for a stonemason each time I'm coming into a cathedral, I'm always amazed, because the articulation of understanding load path, of understanding the material, is really astonishing. And you've got to understand that this cathedral are made with a material with a 25 MPa compressive strength. So a very, you know, compared to your concrete you have now, or some granite who's got 120, the understanding on the observation that the power of observation of Gothic builders was so astute, so sharp, that they really knew how to organize that skeleton of stone, and I think it's something that you know, it's something extraordinary. So weak stone. So what some people call strength through the geometry. Okay, and you know, from Egypt, Rome, then the Gothic, the geometry is extremely important. And as we are going to move on close after that on some other books, this book is the Villard de Honnecourt, le manuscrit de Villard de Honnecourt, which is I think 30 sheets of a man, apparently an architect, just a journeyman, would just put different design of Gothic architecture that he spotted along the road of his journey, and it's a sort of first bringing on a piece of paper this very first knowledge about stone architecture. Now it's yours, Steve.
Well, so at about the same time, most of the European, Middle Eastern architecture that you see tends to be what we call anti-funicular. So anti-funicular means, or funicular means rope-like, anti-funicular means arches and vaults and compression structures of, as Pierre was explaining, with the Romans, small components of stone forming compression structures, and the Gothic the same. Actually, in India, in northern India, the architecture, or what we understand to be Indian architecture, tends to be of more of that tradition. In the south of India was the Vijayanagara Empire, and Hampi was the capital, and really extraordinary to see stone being used as a flexural material instead of a compressive material. So trabeated structures, beams, columns, stone slabs, 700 years old, hundreds and hundreds of buildings, and quite different and distinct from certainly what we've seen historically in Europe and in the Middle East of compression structures. So a completely different way of thinking about stone as a flexural material instead of as a compressive material.
Karen,
oh, you can do that one.
No, this one is interesting. Go.
Well, so this is... So we were asking people, what is this? And people say, oh, it's a concrete stair. Oh, when? Well, maybe 1930. Actually, it's a stone stair from 1830.
1870.
And it's the Place de...
La Cour des Voraces.
Cour des Voraces in Lyon. And this is a kind of unusual example of European stone as a flexural material, as a beam, instead of as a compressive structure.
So, again, something very interesting. It's 1870. This is, how do you call that? A workhouse? Workhouse, it's called?
Commune.
Workhouse, sorry?
Commune.
Commune, yes, for workers. So this beautiful, elegant structure, we linked all the different, all the different floors. Those components are 150 mil thick. 150 mil thick. And what's important is the design was driven by the thickness of stone they were able to extract on that material. So really the material that guided the design, rather than having someone suddenly saying, I'm going to have this curve here, I'm going to have this organization of my space. No, no, no. They had very little, they had some stone. It was very hard to extract because it's a very, very tough stone from the Lyon area. And as I say, they were coming usually in 150 to 200 mil. And they organized their stairwell using that system. Alors, the good old Philibert Delorme. So I don't know if you know Philibert Delorme, this handsome Frenchman. And we haven't reached still yet the pig beard. That's going to happen a bit later, I think, in some of the slides. But Philibert Delorme was what we called the very first architect, all right? And this very first architect in 1561 wrote this very first book that was a compilation of key innovation in wood, in stone, and what we call stereotomy, the art of cutting volume. And in this little book, the book was how to build well at little cost. I'm sure a book we all want to read, and especially our clients. But what was fantastic with this book is that you can see again another big chapter in the history of stone architecture, is that stereotomy is not just a sort of how to call that an exercise in geometry or tough geometry in 2D or 3D. It's about making as much as possible of your stone. Again, this can only happen in area where stone was quite soft, again, 20, 30 years, 25 MPa, and that you can find and that you could extract in small bits. Okay, so this squinch that is just this square tower in this angle was 100 years or 200 years earlier would have been a succession of corbels, okay, thick corbels on top of each other. But here we said no. I really want to be as efficient as possible with the stone I've got. It's coming again in 200 mil thick, okay, and I need to extract that as much as possible of that stone. Okay, and to extract as much as possible of that stone, you need to be a keen stereotomician and know how to extract not only in that bits of stone, but also in the numbers of phases of shaping your stone. Because shaping stone is going to take you 2, 3, 4 different, from 1 to 20 or 50 different phasing to get your stone shaped. And you want it to be as efficient as possible. So you want as little as possible of this, what we call template, to shape that. So in fact, these little 3-volt cantilevered are just 150 to 200 mil thick. So again, this architecture is driven by the material and the cost associated to it. We are reaching top pig beard here, which we know responds very well, all of 3 here. This is Mr. Séjourné. Mr. Séjourné, he was an engineer, a structural engineer, a French structural engineer, and he details at the end of the 1800 les grandes voûtes. Okay, what's fascinating about this is that you really see also not only, as I say, pig beard, but also pig understanding of stone and how to shape it. Okay, you need a large infrastructure all across Europe, and this infrastructure need to be done for to bring water, to start the how to call that the train rail tracks and so forth. You need bridges. You need tunnel. And when you build a bridge in the middle of France and you don't have a furnace or a lot of wood, you are going to take the material you have the most around you. And most of the case, it was going to be stone. So this engineer devised a 6-volume about bridge building, and to bring France into the 21st century because of the rail. Now, something very interesting is that that bridge was hated by Séjourné. He found it extremely heavily composed, and he said normal archers would have suited. But what I want to say is that really, this is the last big architecture in stone. From then, it's going to be steel, it's going to be concrete, because of several reasons, but here we are really now peak stone. Oh, that's a jump. Is it the one bit after? No?
No, that's it.
That's it?
Yep.
There's none after?
Steve, what have you done?
I don't know.
There's none after?
No, there's more.
A bit after? Yeah. Oh, thank you. So, or you know what? No, the two before.
No,
the two
this
before.
is fine.
No, the two before.
No, let's go with this one. This one's great.
Sorry, the two before. Yes. All right. So, as I say, from 1900, stone is going to disappear from the vocabulary and of the engineer and of the architect, and that is Mr. Paul Abraham, an architect and historian, I think, historian in architecture. And just after the war, in 1947, he decided to write this little book, which is a fascinating book about prefabrication and architectural prefabrication in 1947. And he deployed a completely new system of housing that would be very quickly deployed in the field to house, of course, all the people who had lost their houses during the war. And what is fantastic is that this system were rolled out very quickly. What you can see in the pictures up there is just that he decided not to see elevation as walls, but just as empty windows, and then the walls being built after around. So the building on the right hand side there is in Orléans. He rebuilt Orléans, 3 or 4 districts of Orléans, completely using that system, and that system is used in stone. But if you look at the next one, what he did was, because innovation was key in this period of rebuilding France, and plenty of systems came to the market. One, of course, is Camus' famous prefabricated walls. But this one was very simple. You take a piece of stone that would be prefabricated, you have an outside and inside wall, and then, of course, you put some concrete, rough concrete, being put together between this, sandwiching the natural stone.
So it becomes permanent formwork.
Yeah, exactly. So I can't remember the name of the inventor behind it, but you can see the system. And what was fantastic is that the innovation was just brought into the field very quickly. There were no, I don't know, does it go through this regulation or codes? And does it make really sense? No, you have people in the street, they need to have housing. You know that system is 95% safe, let's bring it into the market.
It's not bad.
I was in Orléans years ago. So now, something when it was going to be rebuilt, one of the problems was, shall I dare to say, strikes. Right. In 1947, the coal miner went into strikes. I wonder why, but those grumpy buggers decided to go on strike, and as such, the French government decided to, because they had to rebuild all these houses and find solution, they thought maybe the best way to go through the rebuild would be to use concrete, cement, steel to rebuild the large infrastructure of France, and maybe use all the material to rebuild this housing that don't demand this material. So they looked at the amount of coal that you need for 1 cubic meters of concrete, and it was 225 kilos, and 10 kilos for exactly the same material, same strength, and of course was rolled out this amazing period of in France from 1947 to 1974, where among Mr. Pouillon, the great French architect, which rebuilt the housing stock in France using stone, prefabricated, pre-cut. Each quarries had a sort of module that they were going to extract using this new machine they put together very quickly and put into quarries, so that you can roll out very efficiently a new kind of load-bearing facade, 250 or 300 mil thick. And of course, he's the writer of Les Pierres Sauvages, among other, a great architect writer who knew the power of using local material.
So from morning to afternoon.
Yes, there is always some legend and myth around this sort of man. But he used to say that he wanted stone extracted in the morning, fitted in the afternoon, right? So.
Amin has explained why we're interested in working with stone, and Pierre has some of the history of stone, the development of stone over many thousands of years. How do we reinterpret stone for modern use? And in some ways, we think about the history when we think about how stone's been used before, and we mimic it, or we adapt it, or we use it in different ways. But also, it's quite interesting to forget about how stone was used before and just think about it as a new material with certain attributes and how it might be used with kind of methods. So the most traditional way of using stone is as a compression structure, and you probably know Heinz Isler, the Swiss engineer, who was an intuitive form finder of compression structures by hanging tension structures, a bit like Gabby, other people. Not hugely mathematical, but doing experiments to discover forms, and using those forms to make buildings brings an inherent economy in the way that the buildings are built. We sometimes, with the students, do experiments hanging pieces of cloth in plaster of Paris, and while they look ugly hung the right way up, actually incredibly interesting and mathematically perfect when they're in compression. We've used this more recently on a project in near London where we're burying a swimming pool underground. So about 3 meters underground is the crown of this thing, and the traditional way of building a swimming pool would be to build a big concrete box, and if you wanted a stone finish on the inside, tile it in something. So we decided that we would experiment with how you can find a form for this kind of vault. So a balloon inflated from the inside being pushed into tension is the complete reverse of a compression structure being pushed from the outside by earth load. And so strapping this balloon to this piece of wood with these bits of string gave us an idea about how we might have a ribbed vault for this
and finding
structure.
that balance between number of ribs and the length or size of that vault. So,
yeah. So this is that thing in construction. It's about 12 meters across. The sheet piling here is temporary, so we make the excavation with the sheet piling, we build the vault on the inside of it, and I think the big innovation here is that we put the waterproofing on the outside, and then we put the insulation on the outside in the form of glaze pour, which is a waste product, foam glass aggregate, which gives the insulation, so you can actually express the structure on the inside of the building rather than have to cover it in additional layers of waterproofing and hide it behind plasterboard or other fake finishes. So you can see that thing standing there before it's buried. The walls here are about 100 millimeters thick, and then the ribs are reinforced stone elements. But predominantly, it's 100 millimeters of unreinforced stone. Had that been a traditional rectangular concrete structure, it would be 600 millimeters of concrete to span across the top and 600 millimeters of concrete on the side. So massive carbon reduction achieved by being thoughtful about the form of the structure. Yeah. Similarly, we were asked to design an exhibit for Clerkenwell Design Week, which is a design festival in London, using the stone bricks that Amin was talking about. When we were initially looking at this, we were presented a scheme for it by an architect with vertical side walls and a radial arch on the top, which requires a lot of stone thickness and a lot of reinforcement. And we were explaining that actually if you adapt the form to a more mathematical hyperbolic arch, you can be a lot more efficient. And particularly the idea about using bricks on the sides of buildings, so if the bricks aren't load-bearing, clay bricks expand, they move quite a lot, you need a lot of movement joints and shelf angles. Most buildings or large buildings clad in clay bricks paradoxically support the walls, the frame and the floors support the walls rather than the walls supporting the floors, which is completely perverse within the context of 10,000 years.
So the superstructure gets even bigger. Foundations get even bigger. Yeah.
So again, here we're thinking about the form. If you scallop the stone brickwork, you can take account the movement joints and the shingles. The thing can stack all the way up because the stone brick is about 10 times stronger than a clay brick. And actually, by creating this articulation in the facade, you don't need wind posts, SFS systems, secondary supports to the masonry, so it can become a self-supporting ground-based thing, which is a huge economy, a huge carbon economy.
Saving in cost as well as carbon, yeah.
So the reason that we put this slide about Hampi into Pierre's section is to say that there are examples of stone being used in flexure throughout history. So all of the stones in Hampi, they're using stone as a flexural material. And if you said to most engineers, and actually to me even at the beginning of starting to work with stone, we're going to rely on stone as a tensile material, I would say, no, that's extremely dangerous. It's a fragile material. That's not going to work. But actually, not only is there Hampi, the example that we gave from the staircase in Lyon, but London is full of traditional stone staircases. So this is one of the means projects. It's not a very traditional stone staircase, but fundamentally the cables there are just for the bow thread enclosure. They're not holding up the treads. One stone tread sits on the other, and the load trickles down the staircase. If you have one tread on top of the other, in order to move out of the way, it has to twist. As it's built into the wall, it can't twist, so it's a torsionally restrained, reciprocating structure. This structure relies on tension, and there are staircases all over London, all over Europe, I'm sure here in Canada as well, where we're using tension, and people are climbing up and down those staircases all day long, and so we think, okay, we're going to be interested, and we're going to use stone as a tensile material. So we developed this idea that you might obviously make a case like that, and we made lots and lots of staircases like that with Pierre in the early days. The idea that you could make the staircase flat instead of steps, so you can make a bit of floor with tiles working in exactly the same static way, and then you can build another one on the side of the first one, and then you can start to create a reciprocating torsional flat structure in unreinforced stone. And it occurred to me after kind of figuring that out that it's exactly like this. So a tile puzzle has no rails or supports in between. The tiles span between the edges of that plastic frame, and they span because they're torsionally locked into the corners, and they're torsionally locked into each other. So if you can imagine, I don't know if I can
I just want to point out that it is not Steve calculator.
Yeah.
Just, it's yeah.
So if you see here, this tile is held on that edge and on that edge, and so these other two edges are stable because it's built on two sides. When you build the next tile in, it's supported on that edge and the previous tile, and then you can put this one in, and it's supported on that edge and the previous tile. So they all interlock, kinetically locked together, and they form a structure. So Pierre and I decided that we were invited to exhibit in the V&A in London in the Raphael Gallery, and so we needed to build something quite quick. This floor spans 3 meters. It's 50 millimeters of unreinforced stone. The little washers were a quick way of locking the stones together without a lot of work. So the bolt goes between the gap in the stones, and there's a diamond-shaped washer above and below. And each tile is 500 millimeters square. Spans 3 meters in both directions, unreinforced. You can jump up and down on it totally stiff. Actually, you can break quite a few tiles before it collapses. Somebody said something interesting recently. Crabs and lobsters, their shells are made of really brittle calcium plates that are glued together with something much more flexible. So you have stiffness and brittleness, but actually the system itself is more flexible and ductile. So here, because of the gaps and the joints and the washers, you have a system which has redundancy. It's not fragile like an eggshell. You can break a lot of the tiles before the thing falls down. I'm thinking that this is actually quite an amazing way of making floor in a building. Moving on with the idea of using stone. Actually, this is Clark and Well Close, which is exhibited downstairs, and it's Amin's own project. This is our Revit model: concrete slabs and a concrete core, and then a stone facade. And the stone facade is entirely load-bearing, so there are no other columns in the building. All the weight of the slabs go down the stone facade. We realized that a stonemason, and slightly on the theme of what Amin was saying in the first place, we are divorced into 3 people, where previously we would have been 1 person. A concrete contractor and a stonemason are 2 different people. They don't work on site together very well because they both want the crane all the time. Were they the same person, we wouldn't have this problem. So we decided that we would divorce the 2 activities in time by building this concrete frame, leaving in all of the backpropping, and then building the stone frame afterwards, so they take turns to work on the building without falling over each other. So you imagine the other way of doing it is somebody comes week 1, builds a bit of stone, they go away, somebody comes week 2, builds a bit of concrete, teams demobilizing and remobilizing is not efficient.
And the whole work took for the stone skeleton took 6 months to build. So it was a very fast turnaround. Plus, as we're talking about the amount of stone needed, we needed here 100 cubic meters of stone. And when it's hard to imagine, but 100 cubic meters of stone is of course 10 by 10 meter by 1 meter deep. It's a very small, borrowing. You borrow very little on the Earth's crust to do the building, knowing that you could bring this stone again later.
So, so the stones are worked as little as possible. They come from quite an arcane quarry where they split the stone rather than saw it. So they split the stone and they roll it off the bedding plane. The joints are full of fossils.
Still on the sedimentary layer. So
you have one finish, the really kind of gnarly stones here where it's been split, and then the other finish where you see the barrels of the blood and feathers going through where it's split vertical to the bedding plane, and then they're sawn up. Exactly the size they need for the structural load. So you see the column on the corner at the top is absolutely tiny, and they get much fatter down the bottom when they get to the bottom of the building.
And counterintuitively, right at the top, they suddenly get bigger again, don't they? Because do you want to explain why?
Maybe that was a mistake.
I think your project engineer said it was because of wind loading.
Oh, wind loading.
It's all very emotional for me to see all the things I told them about stone and talking between them about stone like that. It's very emotional.
But this is completely structural. It's completely structural, and also it's the most pragmatic and succinct way of getting that material and putting it in the building. And the architectural expression of that is all derived from that series of decisions and that process. So it's an aesthetic that comes from the way that it's built, and of course it's very carbon saving because it's stone rather than concrete or steel. Or what it would be a steel frame with all kinds of clips and gadgets and lightweight cladding and bits of polythene and kind of crap all over it. So it's a very succinct solution, whose aesthetic expression is completely aligned with its.
But what is interesting is when Amin designed the building, he asked me, as we need to be honest, it was at the pub. And so when he asked me, in a way, he asked me, can we do that in stone? And I say, yeah, of course, yeah, we can make it in stone. But suddenly, when he asked, well, what dimension? And sheepishly, I don't know, because I had to look at you, the engineer, to know that. But 100 years ago, I would have not turned next to an engineer to ask to have the answer. I would have known, because we would have passed this information from one stonemason to the other. But then suddenly, with that break of engineering knowledge and so on, we lost that spirit in our own material. So I relearn about using stone and digging section through sieve in a way.
Yeah. So not content with this one, finishing this one. This is a building composed of 3 separate blocks, two sort of narrow towers and another block at the back. The access to these buildings is an external staircase, so a lift shaft and a service riser and a staircase, which are unclosed, and they sit between the 3 towers, and so the building has no structural core. So typically, as you probably know, you build a building and you have a lift shaft. The lift shaft is the thing that stops all the building from falling over. There's nothing like that here. So here we're using the stone, unreinforced pieces of granite and basalt form a moment frame that's 10 stories high. When the wind blows, it's the unreinforced stone that stops the building from falling over in the wind. So initially I was thinking, Jesus, do we really want to do that? We're going to have unreinforced basalt, a 10-story building in the wind, and it was quite arresting.
Well, explain because originally it was designed in limestone or sandstone, and we'd sent it for testing, and we realised, okay, we've got the right size.
We had a weaker. Actually, no, it was fire. So we're worried about fire resistance. So we thought igneous rock. Igneous rock is better in a fire. So
who want to worry about fire resistance?
Well, yeah.
So it's double the height of Clerkenwell, so the fire requirement was double the amount in hours.
Yeah.
So we could double or quadruple the amount of limestone, but then I think Pierre said, well, you can try basalt, born from fire. Let's test that. It was quarter of the amount of the material you need. So quarter of the amount of the extraction, quarter amount of journeys on by truck and lifting.
And a much stronger material than the Clerkenwell material.
Yeah.
But with the structural question, you think, oh, it could fall down, but actually then you start thinking, what would have to happen for this to fall down? So we start looking at the redundancy in the building. We would have to have, so this stone has a factor of safety of about 3. We're using the lowest expected values, so there are stones that are much stronger than the value that we're using, and we have a factor of safety of 3, and we would need all of the columns on a single level to fail simultaneously for the building to fall over. And when you start thinking about that happening, you think, no, actually, that's probabilistically impossible, and it gives you a sense of thinking about how a building stands rather than how it might be. The key building is the way that the stones are connected together. So the moment connection between the beams and the columns, connecting columns with the beams in a castaway, cross connections is very important. So there's a steel bracket, firmly broken from the concrete slabs on the inside. The stones wedge in on either side, and they're tied vertically through there by a tie. Here's a sketch of ours showing how that's put together. The thermal breaks in here. This angle that connects it is cast into the slab. The stones fit in either side, and then that bracket's completely absorbed into the mortar in the joint, and you can't see it on the outside of the building. A few shots of that building being built and slowly appearing from the.
Have you got photos of the lift shaft? Or
Yeah,
just built it?
I wasn't going to dwell on that too much. The lift shaft needed 1 hour and 20 minutes of fire resistance, and was going to be a steel frame clad in 4 layers of plasterboard on the inside and the outside, very, very expensive. So as a cost-saving solution, we built a stone lift shaft from single-story slabs of lavakite granite, 100 millimeters thick. They prefabricated each level in a goods yard outside of London. They delivered them, and they built a 13-story lift shaft in 1.5 days in stone. So that was quite an orthodox achievement. Because of changes in the design, some of the stones didn't work, so we had to add in a bit of bracing here and there, but for the most part, it's unbraced. And yeah. So that's using stone in tension. Stone can only do so much in tension, so what is the next thing that we were going to look at? Reinforcing stone, post-tensioning stone. So this was an early experiment. Stone is much stronger than concrete. Concrete shrinks and creeps because it has a lot of water in it. When it dries, it starts to move. Stone doesn't have that problem. Stone's much stronger and much stiffer, so a section, equivalent stone section to a concrete section will be much smaller. So we decided to start off by building this bench, again 50 millimeters thick, spanning 3.2 meters, 2 cables going through it. The cables are on a slight curve, so when they're tensioned, they counteract the dead load of the bench. This is the kind of simple version of the system. We didn't take very good photos of this, I have to say, but 50 millimeters thick, spanning 3.2 meters, is quite arresting as a span to depth ratio. Pierre was in the staircase business at the time, and most of these experiments were done to develop ways of selling staircases for high net worth individuals' houses, which is possibly not our favorite kind of work, but you know,
pays the bills.
You have to earn a crust.
That's a market. Someone has got to do it.
Yeah. So we started experimenting with reinforced stone for staircases. So initially, short, straight flights, longer flights, slightly curved flights, big helical flights, and this was the first really big one. It's a 270-degree helix. Actually, the flight is 1.4 meters wide. It's got 2 cables going through the middle of it, 100 kilonewtons of pre-tension in every cable. Each tread is an individual piece of stone cut by Pierre's team. We did an experiment, didn't work at all.
That's my.
Was it yours?
Yeah.
We learned with this, quite terrifying. Eventually, we figured out, and this is what Pierre calls his torture chamber of staircases. Load testing the 75% model, and we were quite encouraged by this, assuming there was actually water in the barrels. And this is the first. The first really big one. I think we've done probably 60 or 100 of these internationally around the world.
Or 50, now. At least 50. Yeah.
At least 50. It's 120 millimeters deep in the middle, so very, very shallow. And it's just such a succinct solution. The normal way that you would get a staircase like this, put in a steel frame, clad it in some kind of marble with a lot of glue. Stone's going to fall off. It's going to be deeper, heavier, and a lot more work. So the idea that this is just, is what it is. It's a visible structure to what it has to do. I should say that the architect added a rather embarrassing balustrade to this later on.
Not me.
Not you. No. You do good balustrades sometimes.
Thank you. All right. That's what I'm left, balustrades.
This isn't one of our means either, but we've done kind of quite wacky ones.
Alors, by the way, as Marguerite would say, this is not a staircase. Right? Because it's breaking few code regulation in the UK. So this is a sculpture. This is a sculpture which happened to link two floors between each other, on which you can go up from one floor to the other, but it's not
your
a
own risk.
It's not a case.
So we thought we didn't really want to be on this planet to make staircases for rich people all the time, and maybe there was something else to do. The staircases are really complicated. We got a lot of very complex analysis. We did a lot of testing. We had all kinds of worries about it. Actually, beams, columns, and slabs for ordinary houses, much more simple to do, much more achievable, and because of the low carbon and the other reasons, a societal good. So we started working on developing these things. So Sebastian from UCL and Pierre's partner Alex, testing beams to destruction, see how strong they are. I was really, actually when we designed Clark Close, we were saying, oh, well, limestone doesn't burn. Shortly afterwards, I started thinking, oh yeah, shit, you burn limestone to make lime, don't you? So 700 degrees, that means building is going to turn into cement. So we thought maybe we better do some fire testing. This was the first big fire test. It's an 8-meter span beam. It's carrying 2 10-ton loads. It sat on a Friday afternoon outside Paris for what should have been a 1-hour fire test. It survived for 3 hours, making those French fire engineers very annoyed.
Yeah.
And eventually it didn't collapse. They closed it down. Yeah. And when concrete, again, because the water sat inside the concrete, when you burn concrete, the water turns to steam and it blows the face off of the concrete. So you get explosive spalling, it exposes the rebar melts, and the beam falls down. For some reason, limestone doesn't have those truncated vents. The steam freely vents. We didn't get any explosive spalling. Because it's a post-tension beam, the reinforcement is a lot further inside than it would normally be, so it's not as exposed to the fire. So we got 3-hour fire resistance from this beam, and very encouraging for Amin's building, which we'd already built. Somebody said, this is the previous New Stone Age exhibition in London, and this was the exhibit that we put outside the building on the front. Amin had been talking to Olympia in York, maybe, or Candy or some developer, Canary Wharf Developments, and saying if we wanted to commercialize stone beams for commercial use or for commercial buildings, what would they need? They said we need 12-meter column-free spaces. I don't know why in an office full of meeting rooms and desks they need 12-meter column-free spaces. Friday night roller disco, who knows? So anyway, we rose to the challenge. It's 12-meter span, 450 millimeter deep by 200 millimeter beam, 75 millimeter top slab in stone. They work collaboratively together. So when the beam sags, it compresses the top slab. So you can see these slightly castellated top profiles so that they're pushing compression into the top level. Just to demonstrate how simple it is and how easy it is to make a stone beam to replace a steel beam. So this has about 10% of the carbon footprint of the steel beam equivalent. So that's massively less. And if you think about the processes involved in making a steel beam, digging up millions of tons of coal in Australia, taking it to India for a blast furnace, taking it to a blending mill and a rolling mill and a fabrication shop.
And that's just the beam without...
That's just the beam without... But you can, Pierre, with the tools that he could fit a suitcase, could go to a quarry and make this beam. So a very succinct way of building structure. We put something in the Royal Academy Summer Show, another example, a 5.5 meter cantilever, 200 millimeters deep, with cables on top. And we like the idea of ironically supporting stone on timber, rather than the other way around.
That's 11 meters long, yeah?
It's 11 meters long. Well, we wanted to have a 5.5 meter cantilever, and we thought, what could we fix that to? And the most logical answer, another 5.5 meter cantilever. And then we were worried, actually, that if somebody got on the end here and started hanging, they would pull the whole thing over. So it freely tilts. So if somebody grabbed it, it would just seesaw back and forth. So it's a kind of flexible thing. We won the architecture prize for that. And then this is... yeah, do you want to talk?
Yeah. You want to talk about it?
That's all very interesting, Steve.
I got there first. I'm sure what you're going to say is going to be very interesting.
Okay, so learning from the various other projects, we got this commission, which expanded to, for a very, very extreme, you just won't believe the budget, something like 250 million, where we decided, hey, fine, we'll experiment with, the pool was one of them, so this pool dug in the side of the hillside. But if you can see these bolts, these are the pre-tensioned floor slabs that we experimented with Canary Wharf, that are actually, some of them are 12 meters, some of them are 14 meters, linked beams as well. The client actually liked to express. So this project actually does experiment with more. Stones that are just simply stacked on top of one another, grounded into place. Pre-tensioned floor slabs where they liked the idea the underside was just rough, the top left smooth for finishes. Pre-tensioned beams here that support those, also left expressed. Whose slides are these?
Mine. Thank you. This is Ibavi. Ibavi is the housing institute of the Balearic Islands, and there was a guy there called Carles Oliver who wanted to reintroduce local materials and to lower carbon in housing. So traditionally in Mallorca, they would build with Marés sandstone, which is hugely available on the island because there's sandstone absolutely everywhere, and they would build with that stone. But more recently, they've been building with concrete in an international style, and they wanted to get away from that. So they wanted buildings with high thermal mass that didn't need air conditioning, using local materials. And his comment was, there are 7,000 spoken languages in the world. Why aren't there 7,000 architectural languages? Architecture should be specific, should reflect the local resources and the local conditions rather than being just ubiquitously steel, concrete, and glass. So I started thinking about this and thinking when we're building in the UK and when we're thinking about building sustainable buildings, we're building CLT. And CLT, cross-laminated timber, very timber-hungry, not particularly efficient, solid slabs of wood. I think you also manufacture in Canada and use quite a lot. This is not what we have in the UK. So neither of these things are really a UK culture because we don't have massive quarries and we don't have massive supplies of timber. So I was thinking what would be a good vernacular for us. So the UK, not that hot, not that cold. Many buildings are air conditioned. If the building is very lightweight, then it definitely needs to be air conditioned for some temperatures which are increasing. But the building has thermal mass, it doesn't need to be. If people want to put thermal mass in the building, if you build it with a lot of concrete, you put a huge amount of energy into the building, much more than you'll ever spend on air conditioning, so it's completely pointless. So we were trying to modulate just enough thermal mass to remove the air conditioning with an otherwise low carbon frame. So this is a building for the Anna Freud Foundation. All of the above ground structures are a hybrid concrete and timber frame. So we're using LVL Baubucher beams connected to thin concrete slabs, compositely connected. So when the wooden beams flex, they compress the concrete. So the concrete makes the wooden beam stronger. And we built that building without any air conditioning. So it works like this. Those structures are exposed inside the building. The windows are actuated, so they open at night, and the building cools down, and they close up in the daytime, and they keep the cold inside. So it's a very low carbon way to build. It's lightweight, it's quite quick, and it gets rid of air conditioning. So we're thinking the only issue with this is the concrete, and obviously we're working in stone. So the next step is, can we just replace the concrete with stone? Sorry, did you have something?
No. What I want to say is that when you go down and did the exhibition, you can see the system in place put by Bamberger, Nathanstein, where you got your wood, that beam with the stone on top. And what you've got is the desk downstairs, and that's a representation of what you can see.
What looks like a table, what looks like a bench, are actually the floor systems.
But that's the way.
Yeah, so using the stone is a particularly local response to the UK because we have small format stones in reasonable abundance. We have joists, rather than CLT. We have limited timber, not that much timber. So here you put these two things together, and actually it's perfect for the climatic conditions within the building, and it's a very, very low carbon way of building, and actually quite interesting to look at. So I think this is a great vernacular for the UK, a post-tension stone beam making a long span. So on this building here, you can see post-tension stone beam. We like the irony of having a wooden post holding up the end of the stone beam, timber joists running back into the building, and then this combination of timber and stone in the ceiling is a great way of building, and actually has the potential to build quite big buildings, quite long spans, quite lightweight for commercial or residential. Another one, Niwa House. So we've got several buildings. We normally start with a very small one with a new idea, and we kind of graduate it. What other systems could there be? So looking at what's that Egyptian custom?
Who?
Haptotech.
Sorry?
The Egyptian
Imhotep.
So he's turning reed architecture into stone architecture. So he's switching from reed to stone, but the stone still carries the flavor of the reeds. When there are major paradigm shifts in construction material, people always like attached to the last one. So Iron Bridge in the UK is the first cast iron structure. All the detailing is carpentry detailing. So they have little wedges and mortars and tenon joints. All they had in their heads was carpentry, and for them, cast iron is just a new kind of wood. When they first started building with concrete, they're building neoclassical buildings and neo-Gothic buildings, because for them, concrete is a new kind of stone. And you can see from what we're doing, that when we think about stone as a new material, we think it's concrete, because everything that we've made out of reinforced stone starts looking like concrete. And you think, yeah, you're really hung up on the prior materials to the paradigm shift. So we were trying to experiment with, if we forget about all historical precedent and stop thinking about it being stone, what could it be? So if it's like steel, you make a stick system and you bolt it together with bolted connections. So it's literally like you're building a steel building with steel beams. Is it this kind of system where we have the long span beams and the composite timber and stone in between? The torsional floor plates from the tile puzzle, we can make big floors with this without any kind of reinforcement. So we had the idea that we could make a post-tension stone column and beam system and put the floor tile system in between it and build actually readily upcyclable buildings quite quickly without formwork and false work, very low carbon. We made a prototype of that in another exhibition. This was a competition that we did with Amin for a bridge in Graz, a hybrid timber and stone truss bridge. We didn't win, unfortunately, but Pierre made a nice big one.
Yeah.
And then really, and I really love the perversity, how lightweight could stone be? When people are imagining stone, they're thinking about castles and cathedrals and really kind of heavy, massive things, pyramids. Actually, stone could be incredibly light. We can use cores of high-strength stone with a kind of piano wire tendon running down the middle of them, and we can make very efficient compression structures. And in space frames, buckling and stiffness are the primary concerns, so you put a lot of steel in for buckling and stiffness. If we make that stone instead, then this structure would have 75% less steel and a considerably less carbon. So we developed a slightly not particularly sophisticated node system and made this as an exhibit for the Royal Academy in London as a sort of demonstration of how it might work. But the idea is that this really opens up the field to making grid shells, pylons, trusses, other kinds of framed light members with stone, instead of thinking of it as a really massive material. So this kind of Zaha Hadid building, this kind of structure could be, in part at least, a stone frame shedding a lot of the carbon. We're working with in the north of Spain to a node system, so we were looking at how we map the node system and use that for grid shells. Over to you.
Yeah. Sorry. Right. So I think we're all educated enough to know where stone come from. It's a sedimentary material whose dead animal matters most of the time when it's limestone that is gathered at the bottom of the ocean or lake or river, and through compression, through reheat, you are going to get some standard limestone, or it can be crystallized through the reheating of the material closer to the mantle. And depending on how fast it's going to get
cool.
Thank you. To get cooler, it's going to change its property. So you've got travertine, you've got marble, and you've got your standard limestone. Here on this project, this is the beauty, as I said, is to pass a block of stone from one generation to the other. This is a refurb stone from a postmodernist building in central London, and when we've got a bit of spare cash, we buy those blocks because they are 300 mm, 1 meter long, 600 mm wide, and it's quite it's again an already made quarry that we have in the yard, and we can get at a good price. The shaping is now done using mostly electricity, because I think in a lot of your calculation, I mean, you need to have electricity rather than
diesel. Or?
Yeah, yes. Yeah. And it's key. So we are using here mostly electricity from the grid, and here you've got a typical wire, diamond wire stem. To cut the stone, you've got a single loop. There's some diamond attached on that cable that turn at a certain speed and cut your block like butter or cheese. That's what the one I presented before is what's called a primary cutter. So it's going to cut your slabs in a certain thickness, and then after that we are going to use the other possibility is those large saw that's going to cut through the blocks to do what we call cut to size piece of stone that will be used later on a building. And here is the assembly line that we now have in place at the workshop. You can see here we've got rigs on which we fit our stone. We've got all the bolt dividac bars, the rebars that goes through the columns. Usually it can be 2 or 4, depending on the loading. And we do all that prefabrication off-site. That's very important. We do everything as a prefabricated structure off-site. So that's, some of beams and structure. Some stone slab for another project.
So imagine if that was a steel beam, you'd have to have a giant forged huge factory compared to Pierre's platforms. Yeah.
So here you've got some of those beams at our yard.
This is what's going up.
Oh yes, that's the structure that's going to go up outside. That's the stone demonstrator. You want to talk about it?
No, you go ahead. This is.
Well, I was not.
Oh, sorry, you want to say?
Yeah.
No, he's fine. It's fine.
Yeah, it's fine. So yes, you want to explain that?
Yeah. So so 15 years. This has been a 15-year-long sort of collaboration, getting our brains together and experimenting on trabeated structure, which is untensioned, to eventually pre-tensioning columns and beams, which we realized uses a lot less material, meets more codes, not just for fire, but also ductility in case of failure, and maybe on very well off people. But actually the material and its fabrication is incredibly cheap. So why not begin to roll this out for standard concrete frame, steel frame construction to lower that carbon on more ubiquitous and widespread structures? The Design Museum has government funding for what's called green transition. How can we green transition all design and construction? So they pay for a decorator that allowed this to be fabricated at Earl's Court. And we made a simple column and beam frame that replaces the equivalent of a concrete frame for residential or commercial buildings, with steel end plates So the whole thing could be prefabricated, lifted into place, and connected by standard contractors, as if they were putting a steel frame together. So what you see is columns and beams prefabricated, as well as one of those pretension floor plates that carry on. And then different floors, floor constructions. Right at the top, you've got Dow laminated timber for a floor plate, which I think is about 250 millimeters. The next one is the timber joist with stone sandwich panel on top. You'll see that downstairs are the benches and table. The next one down is the pretension floor plate, which is 150 millimeters of stone with just 2 cables running through it. And then the combined hybrid on the foundations also stone. The whole purpose of this is to demonstrate to Elscourt and other developers in London who've got, Elscourt have got £20 billion worth of development construction going on for the next 15 years. A lot of it is low-rise, mid-rise, and some of it's at 20 or more stories. Most of it can be replaced. So on purpose, it was not meant to be looking spectacular, that interesting, and people think, well, how do I apply it? And they struggle with common application. So we made it deliberately as dull as possible, stone and brick facade, a frame behind, so people immediately understand, oh, it's a standard, it's equivalent for concrete or steel frame. And bricks standing alone as a supporting facade that are just held back to the frame with different floor plates. And then in the garden next to it, the brick garden, again, stone walls, stone lintels, and sills, window surrounds, and the rest of it. So Elscourt bought the stone idea, the idea of stone bricks, the same price as a 5-clay brick, any colour you like, but they're 98% less than the body carbon. So it's a fairly easy choice. Just get bricklayers to do it. We were being overly clever initially, thinking we'll have them at different sizes according to health and safety diagrams, but they quickly told us this is nuts. You've got 5 different sizes. Our brickies is not going to wait for different pallets and understand that this course has to go here. Just make them standard bricks. We eventually realized that the UK, we did some research, and we found out the UK buys 2.5 billion bricks a year, new bricks. We don't make enough of them. We had to do a presentation to BlackRock, about decarbonising the future. We told them that the UK doesn't make enough bricks. Go for stone bricks, start buying quarries, buy bits of forest as well. You'll have a future of decarbonised construction. They were furiously making notes. A year later, they announced it'll be easier and cheaper, quicker return if we just invest in existing 5-clay brick factories as opposed to marketing stone bricks. Oh, fuck. Wish we hadn't given them that information. Nevertheless, there are plenty of some quarries have realized we do not even have a toe in that market, let alone a foot in it. So suddenly 15 quarries in the last few years have gone hell for leather, bought the equipment, and now making stone bricks. And slowly but surely, architects are substituting their 5-clay bricks. So that's one side. The next challenge is let's replace steel and concrete frames too. Okay, so we're doing the equivalent demonstrator over here. At some point, it'll be up in the what do you call it? Belvedere. It'll be up in the Belvedere. Except instead of making it totally boring, it's sort of semi-exciting. Steve or Pierre, would you like to?
So we, a little ode to Canada. It's stabilized by logs, and it's built on a boulder.
Well done, Steve.
That's not
We
funny
just,
in Canada, is it?
we just want you to be bold over. Bolder? I know.
But yeah, we're trying to show the big cantilever. It's a sway frame. It's mixed up with timber and the kind of fun of the weight of the cantilever holding up the back column on a tie. The cantilever.
You said the fun.
The fun of the cantilever.
Yes,
the fun of the cantilever.
Because unfortunately, I left both of them with a pencil and some paper. And as I was telling them, we need to do really something simple. And they told me
you should have seen the early sketches.
The early sketch, yes, I
No,
know.
it started as 2 simple structures, and I think Robert wanted it to be
Yes, it's
combined the 2 structures. That's why it's.
scary slide, isn't it?
So it's
What's this
fascinating. I think what's fascinating with stone is that suddenly it put us back into a place where sometimes we don't like to be, which is being squashed into a sort of eternity. And here you've got two eternity. You've got the eternity of the sky, you can see on the left-hand side. So that's a picture from the Hubble telescope. And on the right-hand side, it's a piece of stone, right? It's a piece of stone that has been highly polished.
Not to mention the eternity of our presentation.
Yes, sorry.
Almost over.
And what I find something extremely exciting when you talk about stone is that suddenly it put us human in our place. Sometimes it can be exciting, sometimes it can be scary, but I think that being stuck between the slow time and the deep time of geology and being stuck in front of the eternity of the universe, I think it's a beautiful way of reconnecting with what nature is and just have a lot more responsibility on the way we are using those materials. So that's it.
Oh no, I'm looking. Thank you.
Did you guys wear yourselves out?
Not yet, I think.
Not yet. Maybe I'll keep the questions short, but thanks so much. That was fantastic. I was sort of thinking when you started out by mentioning Vitruvius, if I could assign utility, firmness, and delight to each one of the three of you separately, but I realize that the collaboration doesn't allow for that set of distinctions, especially, Steve, since the other day, you were talking about a lot of practical things, but actually you showed some pretty wild inventions. Anyway, I was struck by, actually, there's so many ways to think about what you guys are doing, and also some of the questions and challenges. Some of them are very prosaic, but important to ask, and others, maybe more highfalutin, but maybe I'll start with the highfalutin. I was struck by Steve, the way you described the sort of, I guess, the holdover of older ways of thinking that make their way into new technologies or new techniques, and like the papyrus capitals of the Egyptian columns, and how that is shaping the way that you all use for. I mean, even the solving problems still do an imagination which is by maybe prior technologies, and that is an observation that I think is fascinating, but also in some ways it strikes me that it is, when I was thinking, when I was first thinking about it, when I've been looking at it for many years now, is that the fact that you're making stone do things that seem unstone-like is one of the things like that's the source of the delight. And that's about you guys come up, you're sort of evangelists. You start with all these data and numbers that explain why to do good, we must do these things. But you are making, I think that's very persuasive. There is this other, say, impact to it as well, and it's harder to talk about it. It's not through which you persuade, large industries to make changes, or policies and things of that sort. But I think that somehow familiarity you're doing with stone is part of what is a sort of delight in the stone. And I know this doesn't really sound like getting into any kind of question. I do have a hard time answering questions sometimes.
It's an interesting question.
But I will make one observation. There's a, I think it's an article by Colin Rowe about the work on means in North. And he talks about how for kind. He can't actually address modern building problems and modern programs because the deep section is unacceptable. You can't waste section. You're not going to build multiple stack up and so forth. And then, you know, of course, here's some uses of crown hall. This is crown hall. It's empty. You need divisions in it. But anyway, you guys flat section stone that span, you know, distances. And that's what looks crazy to me when you're talking about tiles, the reciprocating, so that you can look up and when you rough stone, and it is spanning distances that are not like stone. You know, they're not hammered, like, you know, the surface active forms in the shelter, and those tension the beams, and you're getting these losses, like, you know, in response to the floor plate size requirements that you have for what was it, an office building?
Yeah.
So anyway, there's just, you know, you talk a lot about problems, but in some it is experience unexpectedness of performance that is a site of what is quite remarkable, I think, in my achieving. So maybe more of an observation, but thoughts on that.
Students. Hours mastering and then obviously the connection with the fixers. The idea that I mean, the mastery of that skill allows you to behave in a way that's improvised, that might then lead to innovation. The rest of that, you're enjoying it. It's no longer that conscious. Some of it is about having fun, but knowing you don't even need to know now you're doing good with it, but you're enjoying it and keep testing it at its limits depending on the client you have.
I think it's very much we enjoy with all the things we do. We challenge each other. You know, I do believe that design is going to work. I'm pushing both of them, and I think it's an enlightening dialogue we always have. And but definitely, of course, we are showing and the work, and I remember that's doing that. You know, it's all of fun. We don't have fun in everyday work. I think we are really missing, and that's definitely this experimentation we enjoy.
The other, I mean, for me, we're building that.
Yes.
Yeah.
You know, it's not really that architecturally complex. I mean, sometimes it is, but what's interesting, when you look at styles and ages, the naturals come from very particular conditions and constraints and technical solutions, and then later on they turn styles and get adopted styles and views and that. But when the source of architect, how you solve the technical problem, and how that looks in the end. So particularly
That's from his own brain, perhaps. You know, this is a the old story. He's saying that's what Seneca said, like I said.
No, I think you know, just the incredible scribal form, I suppose you could say it uses less than a quarter. But I think, you know, I remember distinction when I was a student and then thinking, wow, that is some wax on stuff. But also that, you know, it's like these kind of invention are, they're more than just solving problems. They are problem solving. They're also leaps of the imagination, which I think are extraordinary. Even the restoration project that you're, well, going to start to build here tomorrow. I mean, why can't do it so far? You're trying to wow us, which I think you will. Anyway, I was at the other end of the spectrum of kinds of things to talk about. I mean, I can imagine a lot of people who may be interested in doing this kind of work. They wonder how you get any of it. And you spoke yesterday with Richard somewhere about 2 days ago, anyway, before today, about, and you made a lot out of that question, that, if the partners, they have to be willing to risk. But here's a question, I mean, it's taken you 15 years to be allowed to do any of the things you're doing. I don't think you want to say anything about how that's come about.
You know, I go through this conversion. I find it protesting that people try to take single risks. You drive on the motorway in your car, 90 miles an hour, one hand on the steering wheel. You let go of that steering wheel, you're done. And if you told someone, hold stick, if you let go of it, then they would be terrified. So it's kind of about familiarity and this tube train, 3,000 volts, 3 feet away from you. There are situations in life where you carry a lot of risks, and they're set, and you know how to deal with those risks. Building is the same. You don't need to be concerned. You need to evaluate the risks and consider and make a decision based on so many scenarios in many meetings, people talking the kind of Dutch auction, learning the most stupid risk, who are the kind of lowest common denominator for that building. I think it's something hugely conservative, and we just need to be more about, what we can and can't do, and not so, not, you can be safe, but you can be safer. You can enough, you can be safer, you can be really, really, really safe, or you can be safer, keep on safe for safety, you just need to be safe. That's,
I think the context that we often base our clients are willing to some of these look like ideas. The context of us being a section socializing about stone, using everybody, making hence boring numbers. What we're trying to do is say, well, here are the systems of stone and hybrid structure meet all the codes. UK codes, European codes, US codes. The world that draws from those codes into a manual, and that's aimed to be window useful and colleagues. At some point, the idea is that's going to be functional for the Institute of Structural Engineers. And the idea of that is de-risk the stone for people. But there's that context as well as the context of working where sometimes so sometimes it's actually more often not at all, it's procurement who might go to other small firms.
So the just one two things. It's not a feel, but it's using the setup and put my feeling through his little booklet. What the yes, but what's fascinating is that as a point of through so many years between we and Delorme was devised temporary because he was arrogant, because he was a bit of a risk taker. In 1950, he's an arrogant, very talented risk to always challenge the status quo, and both are just the part, but being the same solution of status quo of tradition, not going and challenging all the as I said, that's very fascinating to see that in a way at some point pushing things. But I think we are not that risk. We always rely on each other to when we are pushing too much, and because of the responsibility it was applying to build. So it must be.
We had this whole battle around the stone. We're going to try to show it again. Yes. On a hunger strike and finally
It's the biography by an architect, which on the edge of the communist prison. As I mentioned, it's not every kind of autobiography of an architect. So a very special and amazing man.
I'm going to the audience to see if any questions for you guys. People would like to choose others front.
Thank you for a massively presentation. Testing high lows through material to detection of fissures or continuities might is I would do acoustic testing.
We if there's a sophisticated future of the stone, the control of the behavior of the stone and the grading of the stone is incredibly important, and it's something that would need to be developed properly, and it's something that we don't particularly do at the moment. But we look at the stone in the quarry, we take random samples, we break all of those samples in the laboratory, we have this normal distribution of the stresses and behaviors, and we take a 2.5 times confidence interval, 95% safety value based on that. So we sample and we test to get that. I've heard people say they're able to correlate. So the ultrasound velocity not only tells you the density, also the stiffness, and it would reflect flaws within the stone, but some of the weaknesses possibly don't exhibit themselves in that way. So I haven't seen evidence that we can very clearly correlate the ultrasound behavior to the strength, but there is a project there. And because billions and billions of dollars have been spent developing concrete and steel, and we've developed this stone stuff on a budget of about $50. So whenever we think about, what could you do, how could you make it further, there are thousands of opportunities and questions, and if you had funding, research grants, then you could really push a lot further. But we have to come up with very pragmatic, and the ultrasound thing is really tempting. And actually, it has been done a few times, but there's not really a very good correlation as far as I know so far.
So there's tests more like slump tests that are fairly crude at the moment. But you could add that if you're doing, part of the reason we've gone for pre-tensioning long beams is that whose example we're using, the Egyptian example, if you wanted those long spans and single pieces of stone, you're limiting the quarries you can go to, and the cost goes up. And really, do you want that to happen anyway? Do you want large spans and single pieces? You're limited. Plus, also, you have to super compensate for any potential failure. So you can get weaker stone and pre-tension there. So at that point, the testing is
not so important.
Yeah. And lastly, Arab have been developing testing for the Padre Pio Church in South Italy in 2002 or 3, using ultrasound system. So they were able to check the integrity of the material, not its capacity, but definitely to check its integrity. You would be using exactly the same system that you use in concrete testing, not ultrasound and so on. You can transpose that to stone to check the integrity. So that's been rolled out in several projects already. And I think, as Steve says, with more money, we could definitely improve the grading of stone.
I'm sorry, just I'm getting messages. If we don't, you're running a little late. If we don't wrap up, then we won't get to eat dinner. So I'm going to have to thank you guys for an amazing presentation and several days here. Thank you all for coming.
Thank you.
And I hope to see some of you next weekend. Just a reminder, it's also